Now let's talk about the conformation of alkane. So what do we mean by conformation? Conformation means the spatial arrangement or the arrangement in space for the alkanes. So we know that alkanes are all have sp3 hybridized orbital for the carbons, and the bond angle between the hydrogen carbon hydrogen or hydrogen carbon carbon is 109.5 degrees. They all bonds are sigma bond. But there is also the possibility of rotation between these two carbon atoms, the bond between the two carbon atoms that has a free rotation. And the free rotation will generate what is called conformation. These are the different spatial arrangement of the atoms in space. So conformation of a molecule are the three-dimensional arrangement that differ only by rotation around a single bond. So if you look at these two molecules here, they are the same. The same. They both are ethane, C2H6, and for each carbon, the carbon-carbon bond, there is a free rotation here. And if you notice that all the hydrogen on the carbon are color coded, so we have hydrogen A, which is in red, hydrogen B in green, hydrogen C in blue. As the rotation takes place, you will find that now the hydrogen C here that was in front of us, facing us, this is why we draw the bond here as wedge like this. So which means that in space this is facing us. Now this hydrogen C has become at the back there when the rotation took place, because when we draw a bond in a dashed form like this, that means it's at the back. And hydrogen B that was at the back, now it's at the front, and hydrogen A, instead of being at the top here, it became at the bottom. So there is now a different arrangement of the atoms around the in relation to the other carbon and its connections. So again, to represent this, so this is the first form that we will have, which is called the staggered form. So if you imagine that you are looking from that side here, okay, so you are looking this way, and now the carbon-carbon bond will rotate. If you notice that this blue hydrogen here, there is nothing opposite to it on from the hydrogen on the other carbons. So the other hydrogen, the blue, red, and green, are far away from this hydrogen. As it rotates 60 degrees, you will find that these two blue hydrogens now are just behind each other now. So the first form, where the hydrogens are kept away from each other as possible, it's called a staggered form. And when they are just behind each other this way, it's called an eclipsed form. The eclipsed form here, these two hydrogens and also the green ones and the red ones, as they are the closest they can be in space to each other, there will be some repulsion between them. And so this rotamer or this conformer is called, which is called the eclipsed form, will have an energy maximum, while the staggered form represent the form the staggered rotamer represent the kind of rotamer where the hydrogens are kept as far away from each other in space, so they represent an energy minimum. There is no repulsion here as much as there is repulsion you can see in the eclipsed form. Again, if they rotate another 60 degree in this direction, here as you see in this direction, if it rotates again, we will go back to the staggered form. Even though now the staggered form, the atoms will be placed in different positions, but they are still all hydrogen, and all the atoms are kept away as much as possible from each other. So to represent this kind of bond, we represent it with what is called the Newman projection. So the Newman projection, it can visualize the conformation of a chemical bond from front to back. For ethane, we have two carbons. So carbon 1 and carbon 2 all have 3 hydrogens. So for the first carbon, this is the front one. If you are looking this way, say that you are looking this way. So this is the front one. We will represent it with a dot, and all these three atoms will be represented like this. So the back carbon, the other one, this one, will be represented with a circle, and the three hydrogens here will be represented on this circle. Now let's have a look at this one shape that we just drew. This is the Newman projection. This shape, as you see, all these hydrogens are away from each other. There is what's called the torsional angle or the dihedral angle. The dihedral angle here will be 60, and the dihedral angle here will put the hydrogens as further away from each other. The other form, let's see the other one. So if we rotate this, so again, the front one, front carbon with all three hydrogens, and then we draw the back one with all the three hydrogens here and here and here. So the back hydrogens, if we try to color code them with, let's say, with this orange, you'll see that these back hydrogens are just behind the front one, which means the dihedral angle now is 0, and the all the hydrogens are the closest as they can to each other in space, and this is called the eclipsed form. This eclipsed form represents the highest energy of all rotamers. Again, as we have been explaining here, so if you are looking this way, so the front one is this one, and this is the back one. Okay. The front one has all these three hydrogens, the blue, red, and green, and the back one has the hydrogen here facing us, and the blue one at the back, and the green one at the bottom here. If you look this way, you will find that the hydrogens are not behind each other, but they are furthest away from each other. This is called the staggered form, or the staggered conformation, or the staggered rotamer. As we said, that the staggered one will represent an energy minimum, and the eclipsed one will represent an energy maximum, because there is no repulsion between the hydrogens. The hydrogens are kept as far away from each other in space compared to the eclipsed form. So if we start with the staggered form, okay, with the tetrahedral angle 0, and then we rotate 60 degree, we will end up with the eclipsed form where the atoms will be just behind each other. And then if we rotate another 60 degree, we'll end up with another staggered conformation or staggered rotamer. This is a representation of the potential energy for the different rotamers of ethane. So we start off with a tetrahedral torsional angle of 0, and we start with the staggered form, this one, staggered form, okay, and then this represents an energy minimum. As we rotate the carbon-carbon bond 60 degrees, then we will form the eclipsed form here, which is considered as a transition state because it has an energy maximum. The difference between the energy of the staggered form and the eclipsed form is 2.9 kilocalorie per mole for ethane. It's different with different compounds. If you rotate another 60 degree, we will go back to the staggered form again. This is the second staggered form. And now we color coded one of the hydrogens with red, so you can see how it moves around. So it's first here, and then the red hydrogen is here now. And then as you move, it becomes at the bottom. And then again, if you rotate it 60 degrees again, we will go back to the eclipsed form. This is the red hydrogen, and it keeps on going until we rotate 360 degrees to come back to the same structure like the first one. So the first one and the last one are exactly the same, the hydrogen, red hydrogen in the same place. So at this stage, this is what I want you to know about the conformation of the alkanes. Of course, it becomes more complicated as you have more substituent, not just hydrogen. And but at this stage, this is what I want you to learn about.